We'll start in 1 minute. Today we'll continue in section 8.3 on moments and center of mass, or centers of mass. Okay, so yesterday we were just about finished with the formulas for the center of gravity, or the center of mass, or the centroid. So in this setting, we have a continuous function, y equals f of x, that is above the x-axis. And the region defined is the area. It's the region below the graph of y equals f of x, and above the x-axis, and between the vertical lines, x equals a and x equals b. And yesterday, we derived this formula for the moment of the region about the y-axis. And it's this definite integral. The integrand is rho times x times f of x dx, and the limits are from a to b. And then the moment about the x-axis, the moment of the region about the x-axis, is this formula. It's the definite integral of rho times 1/2 times the square of f of x dx from x equals a to b. The mass of the region the mass of the region is just the density rho multiplied by the area. So the mass m, lowercase m, is rho times the definite integral of f of x dx from x equals a to x equals b. X equals b. This is just this definite integral that we're multiplying by rho is just the area that's below the curve. And so by definition, the centroid, or the center of mass, center of gravity, is denoted by the ordered pair x bar, y bar. And the x-coordinate of the centroid is the moment of the region about the y-axis divided by the mass. But this is In the numerator, it's the definite integral from x equals a to x equals b of rho times x times f of x dx. And in the denominator is the mass. You can put the constant rho on the inside or the outside of the integral. It doesn't matter. But since rho is a constant factor in both the numerator and denominator, they cancel each other out. So we can just write that the x-coordinate of the centroid is the definite integral of x times f of x dx from x equals a to x equals b in the numerator, and in the denominator is the definite integral of f of x from x equals a to x equals b. Okay, this is a formula that you should memorize for the x-coordinate of the centroid. And the y-coordinate of the centroid this is the moment of the region about the x-axis, m sub x, divided by the mass. We know that the constant rho from the numerator will cancel with the constant rho from the denominator, so I'll just write the ratio of integrals without the constant rho. So in the numerator, we have the definite integral of 1/2 times the square of f of x dx from x equals a to x equals b, and then divided by the definite integral of f of x dx from x equals a to x equals b. Yeah, so like I said, memorize these formulas. If you don't memorize them, you can always derive them the way that it was derived before this. Okay, on the next page, back to the lecture notes. So we'll just summarize what we did. Let R be the region in the xy plane with uniform density rho between the graph of y equals f of x, the x-axis, and the vertical lines x equals a and x equals b. The moment of the region R about the y-axis is denoted by capital M sub y. So here we get a chance to see if we can remember those formulas. So this is rho times the definite integral, lower limit x equals a, upper limit x equals b, and the integrand is x times f of x dx. The moment of the region R about the x-axis is denoted by capital M sub x, and it's equal to rho times the definite integral from x equals a to x equals b. The integrand is 1/2 times the square of f of x dx. The mass of the region R is lowercase m. That's equal to rho times the definite integral from x equals a to x equals b of f of x dx. Okay, then the location of the centroid is x bar, y bar. So it might be useful to memorize before writing the definite integrals, just write down the definition of x bar. That's the moment of the region about the y-axis divided by the mass. And we know that the constant rows will cancel, so we'll just write in the numerator the definite integral from x equals a to x equals b. The integrand is x times f of x dx. And then we divide this by the area of the region, which is the definite integral from x equals a to x equals b of f of x dx. Y bar, the y coordinate of the centroid, by definition, is the moment of the region about the x-axis divided by the mass. So y bar. And the rows cancel, so the numerator is the definite integral from x equals a to x equals b. The integrand is 1/2 times the square of f of x dx. And divide by the area of the region, the definite integral from x equals a to x equals b. The integrand is f of x dx. Here we'll look at some examples. So on the next page, find the location of the centroid of the region bounded by y equals sine of x, y equals 0, for values of x between 0 and pi. Okay, let's find the moment of that region about the y-axis first. Okay, we'll try not to get too lackadaisical. Let's include the uniform motion constant rho multiplied by the definite integral. What are the limits for this definite integral? You can just blurt it out if you want. So the lower limit is x equals 0. The upper limit is pi. Hey, what's the integrand? So you can type that in. That should only take you 5 seconds. So on the previous page is the formula. You can look at the formula. Okay, there's an answer online. X times sine of x. In general, x times f of x. So x times sine of x dx. Hey, what's the moment of that region about the x-axis? This one is rho times the definite integral. The limits are the same, 0 to pi. And what's the integrand for this integral? Well, on my formula sheet, I have 1/2 times the function f of x squared. Yeah, so it does involve sine of x squared, but we also have a factor of 1/2. So 1/2 sine of x squared dx. Hey, then the mass of the region, this is rho times the definite integral from 0 to pi of sine of x dx. So the mass is just rho times the area of the region below y equals sine of x between x equals 0 and x equals pi is the definite integral of sine of x from 0 to pi. Okay, there are 3 integrals. I'll do 1/3 of the work. I'll compute the mass, and you can do the other 2. So the mass, an antiderivative of sine of x is negative cosine of x, evaluated from 0 to pi. So we get rho times negative cosine of pi minus negative cosine of 0. Cosine of pi is -1. So the negative of -1 is 1. And we're subtracting a negative, so that means we're adding the cosine of 0, but the cosine of 0 is 1. And so the mass is 2 times rho. Hey, what did you get for the moment of the region about the y-axis? Well, it looks like we're going to use integration by parts to integrate the integral x times sine of x dx. So we can do that down here. Let's just look at the integral of x times sine of x dx and integrate by parts. So if we let u be equal to x, so du is dx, and then dv is sine of x dx. And consequently, v is negative cosine of x. Okay, so u times v, so x times negative cosine of x, I'll write it as negative x cosine of x. And then we're going to subtract the integral of v du. So we're subtracting a negative, so that's plus the integral of cosine of x dx. And an antiderivative of cosine of x is just sine of x. So our integral is negative x cosine of x plus sine of x. Okay, so we'll use this antiderivative up here. So we'll write down the constant rho and then the definite integral. Sorry, the antiderivative is negative x cosine of x plus sine of x. And we're evaluating this between 0 and pi. Okay, so the upper limit pi, we have negative pi times cosine of pi, negative pi times cosine of pi, plus sine of pi, and then the lower limit is 0. So all of the terms are 0 when x is 0. Sine of 0 is 0, and when x is 0, this is 0. So we're just subtracting 0. Okay, cosine of pi is negative 1, and negative pi times negative 1 is pi. And sine of pi is 0. So rho times pi, I'll write it rho times pi without the brackets. Since we know the mass is 2 times rho, and we know that the moment about the y-axis is rho times pi, now we can say what the x-coordinate of the centroid is. So the x-coordinate of the centroid, it's the region, it's the moment of the region about the y-axis divided by the mass, or rho times pi divided by 2 times rho. The rho's cancel, so we just get pi over 2. See how that works? Okay, now let's find the moment of the region about the x-axis. We have a constant rho times 1/2. We can bring that out front. And then just focus on the integral of sine of x squared. So let's look at that down here in isolation. We'll ignore the constant rho divided by 2 and just focus on finding an antiderivative of sine of x squared. Well, my go-to identity if I want to integrate sine of x squared, then I'm going to replace sine of x squared with 1/2 minus 1/2 times cosine of 2x. Remember that identity? So we'll transform this integral to the integral of 1/2 minus 1/2 times cosine of 2x. And then an antiderivative of this is 1/2 x minus 1/4 sine of 2x. Okay, so we'll use this for the antiderivative up here. if we have space. So we'll use red ink for this one. So the moment of the region about the x-axis is rho divided by 2. And then the antiderivative 1/2 x minus 1/4 sine of 2x evaluated between 0 and pi. So a bunch of things are going to be 0, so that will make things easier for us. So when x is pi, I get 1/2 times pi, or pi over 2. And the other term is going to be 0 because sine of 2 pi is 0. And then for the lower limit, when x is 0, the other terms are 0. So this is all we get. Rho divided by 2 times pi divided by 2, or rho times pi divided by 4. And now we can write the y-coordinate of the centroid. It's the moment of the region about the x-axis divided by the mass. So this is rho times pi divided by 4 divided by 2 times rho. The rho's cancel. Pi over 4 divided by 2 is pi over 8. Okay, the last thing we'll do on this example is sketch the region of y equals sine of x between 0 and pi. Okay, so that's supposed to be y equals sine of x. And we could have guessed, well, it's stronger than a guess, but we could have noted that since this part of the sine curve is symmetric with respect to the vertical line x equals pi over 2, we could have known right from the start that the x-coordinate of the centroid is pi over 2, because the line of symmetry is the vertical line x equals pi over 2. And the y-coordinate, pi divided by 8, well, pi is about 3.14, so this is pretty close to 3/8, a little bit less than 1/2. So the centroid is right about there. All right, let's move on to the next part. Hey, this will be slightly more complicated, but not too bad. If a region R with uniform density rho is bounded between two curves, y equals f of x and y equals g of x, where f of x is greater than or equal to g of x for values of x between a and b, then the centroid of that region is denoted by x bar, is the ordered pair x bar, y bar. And as in general, the x-coordinate of the centroid is defined to be the moment of the region about the y-axis divided by the mass. And the moment of the region about the y-axis is rho times the definite integral from x equals a to x equals b. The integrand is x times the quantity f of x minus g of x. And that makes sense because we're just interested in integrating the region between f of x and g of x. So that shouldn't be surprising. And the mass is just rho times the area. And to find the area between the graphs of two functions on an interval, you subtract the lower function from the upper function. That's what we're doing here. So that's not a surprise. The moment of the region about the x-axis, well, if you're not careful, you could stumble over this if you're not careful with the details. So the moment of the region about the x-axis is rho times the definite integral from x equals a to x equals b, and it's 1/2 the quantity of the square of f of x minus the square of g of x. The thing that might get you into trouble if you're not careful is you might try squaring the difference of f of x and g of x, which is not the same as squaring f of x and then subtracting the square of g of x. So just be careful with this one. And then the centroid x bar, we can cancel the rho constants. So just for practice, the numerator is the definite integral from x equals a to b of x times the quantity f of x minus g of x dx divided by the definite integral from a to b of f of x minus g of x. The y-coordinate of the centroid, y bar, by definition, that's the moment of the region about the x-axis divided by the mass. So in the numerator, we get the definite integral from x equals a to b of 1/2 times the quantity, and then f of x squared minus g of x squared dx divided by the area Hey, let's look at an example of this sort. Okay, find the centroid of the region bounded by y equals x plus 2 and y equals x squared. We're not told what the interval of integration has to be. We have to figure that out. We are also not told which function is greater than or equal to the other function on the interval that we're supposed to integrate over. Okay, but this one isn't too hard. there's a couple of ways we can determine the answers to those questions. An algebraic way is set the functions equal to each other and then solve for x. That tells you where the graphs intersect. And then you can test values in that interval to determine which function is greater than the other. That's the algebraic approach. A graphical approach is just to sketch a graph of the two functions. The graphs of these two functions in this case are not so complicated that you can't see what the interval is supposed to be. So let's see. So on another piece of paper, we'll do both the algebraic approach and the graphical approach. So algebraic. Set the functions equal to each other. So set x squared equal to x plus 2, and then solve. So if we set one side equal to 0, x squared minus x minus 2 equals 0, we can solve this by factoring. The two factors are x minus 2 and x plus 1. And the solutions are x equals -1 and x equals 2. So there's a region enclosed by the graphs of those two functions on the interval from x equals 1 to x equals 2. So the next question is, well, which one is above the other on that interval from x equals -1 to x equals 2? Well, you can probably visualize the graphs in your head, and you already know, but what you can do in algebraic approach, pick a number between -1 and 2, like 0. When x equals 0, y plus, y equals x plus 2 is y equals 2. When I replace x with 0, I get y equals 2. And y equals x squared is y equals 0. Since 2 is greater than 0, that tells us that on that interval from x equals -1 to x equals 2, the graph of y equals x plus 2 is greater than or above than, yeah, it's greater than or equal to y equals x squared. Okay, so on the interval from -1 to 2, x plus 2 is greater than or equal to x squared. Okay, a graphical approach. Now these two functions are pretty easy to graph. Y equals x plus 2. The slope is 1 and the y-intercept is at 2. So this is the graph y equals x plus 2. And then the graph of y equals x squared. Well, just don't let me graph it. So we have an enclosed region between x equals -1 and x equals 2. Okay, let's go back to the other page. Okay, so we know the interval is for x values between -1 and 2. And we want to find the moment of the region about the y-axis. So this will be rho times the definite integral from -1 to 2. The integrand is x times the difference of the two functions, so x plus 2 minus x squared dx. So we'll go ahead and multiply x times x plus 2 minus x squared, and we'll get x squared plus 2x minus x to the third dx. This is not too hard to evaluate, so we'll go ahead and get that done. So an antiderivative is x to the third over 3 plus x squared minus x to the fourth over 4, evaluated between -1 and 2. So we have, when x is 2, we have 8/3 plus 4 minus 16 over 4 is minus 4. And then minus the quantity. When x is -1, -1/3 plus 1 minus 1/4. So these 4's cancel each other out. The 8/3 minus -1/3 is just 3. And then we're subtracting 1 and adding 1/4, so minus 1 plus 1/4. So I get 2 1/4 or 9/4 times rho. Okay, then find the moment of the region about the x-axis. Okay, so this will be rho times the definite integral from -1 to 2 of 1/2 times the quantity. So here we have to square x plus 2. And from it, we're subtracting the square of x squared. Okay, I'm going to bring the factor 1/2 out front, so it's rho divided by 2. And we'll simplify the integrand a little bit. When we square x plus 2, we get x squared plus 4x plus 4. And then we're subtracting x to the fourth. And then we can evaluate the integral. So x to the third over 3 plus 2x squared plus 4x minus x to the fifth over 5. From -1 to 2. Okay, when x is 2, we get 8/3 plus 8 plus 8 again plus 32/5. 2 to the fifth is 32. And then we're going to subtract when x is -1, get -1/3 plus 2 minus 4. And we're subtracting a -1/5, so that's plus 1/5. This is going to take a couple of seconds. So notice the 8/3 minus -1/3 again, so that gives us 3. 8 plus 8 is 16, so let's go ahead and combine those. 16 plus 3 is 19. Inside this other set of parentheses, 2 minus 4 is -2, so we're subtracting a -2, so we're adding 2. And the only thing left is 32 minus 1/5, which is plus 31/5. Okay, 19 plus 2 is 21 with a common denominator of 5. That's 105 over 5 plus 31 over 5. So we get rho times 136 divided by 2 times 5. I'll write it as 2 times 5 so we can write this in lower terms. And 2 goes into 160 or 138 68 times, so we get 68 rho divided by 5. So that's what I get for the moment of the region about the x-axis. Okay, we need to know the mass. So this is rho times the definite integral from -1 to 2 of x plus 2 minus x squared. So we get rho, and then the antiderivative x squared over 2 plus 2x minus x to the third over 3 from -1 to 2. Hey, when x is 2, 2 squared over 2, 4 over 2 is 2, plus 4 minus 8/3. And then from that, we subtract quantity. When x is -1, we get 1/2 minus 2, and then plus 1/3. So this is rho times The minus 8/3 minus 1/3 is minus 3. So 2 plus 4 is 6, minus 3 is 3. And then we're subtracting negative 2, so we're adding 2 and then subtracting 1/2. So this is 4.5 row, or 9/2 row. Hey, we're just about out of time, but we can write down the, I'll use the space down here to write down the centroid. So x bar, that's m sub y divided by m, so that's 9/4 row divided by 9/2 row. The rows cancel, then we have 9/4 times the reciprocal, 2/9, or 1/2. And then the y coordinate of the centroid, 68 row over 5 divided by 9/2 row. The rows cancel, 68 over 5 times 2/9. So 136 over 45. Okay, we're out of time, so go ahead and sign in for attendance.